practice talk for my upcoming committee meeting. I'll be presenting some of my work to some faculty members of mine. My group is interested in assembling nanoparticles using DNA to create these discrete arrangements of nanoparticles. We might call these discrete assemblies. The title of my talk today will be a fluorimetry study of the DNA origami cage templated nanoparticle assembly. So let's begin. It's going to be split up into two parts, motivation and plans, and then of course the past year's work. So let's begin with some motivation. So there are two classes of nanoparticles that I'm going to be interested in, and so of course plasmonic nanoparticles and quantum dot nanoparticles. Essentially, nanoparticle materials have different properties from their bulk counterparts. So it turns out that metallic nanoparticles, such as gold, their electrons can oscillate collectively if there is an incident wavelength with the proper resonant frequency, causing a surface plasmon resonance. This gives rise to interesting properties that I'll talk more about soon. And then quantum dots, this is an example of some of the quantum dots that we have in our lab. Compared to they are semiconductor nanoparticles, and they have different properties from their bulk counterparts as well. Essentially, we can excite the electron in the UV. Here, UV lamp is shining upon or illuminating this sample, and because of the quantum confinement within a nanoparticle, an electron can be excited into discrete states. It behaves similarly to atoms. Of course, it leaves a hole, so this exciton is created. And of course, upon relaxation, it may refluoresce. Anyways, so of course, why we assemble the nanoparticles is because we want their properties to couple. So for the plasmonic nanoparticle assemblies, you may achieve local electric field enhancements. Basically, two metallic nanoparticles can be placed very near each other at the nanoscale, and the gap in between them may be a hot spot if you, again, shine light on it to excite the nanoparticles such that their surface plasmons may couple. And then of course, this has found application in spectroscopic techniques, for example, SIRS or fluorescence. And here I just show an example. Two assembled gold nanoparticles with a tiny nanoscale gap here. They were able to place a Psi-5 molecule in between these nanoparticles, and because of this, they were able to use surface-enhanced Raman spectroscopy and achieve single molecule detection, which is very difficult to do. And they wouldn't be able to do this without the assembly of the nanoparticles. There are a lot of other applications, optoelectronic devices, biosensors, and more. As for the quantum dot nanoparticle assemblies, the fluorescence of quantum dots, it turns out that if you are able to assemble quantum dots such that they are nearby each other, there could be some form of energy transfer. This is, again, similar to the atomic model. If you put atoms together, they can form new properties if they're close enough. Anyhow, energy transfer is something that we are interested in. So maybe it's very likely that fret can occur here, and it's been shown to do so. Anyhow, if we talk about energy transfers, then again, fret biosensor is very popular. So we're talking about next generation therapeutics, and then of course photovoltaics. Energy transfer would be something to study using photovoltaics, and they do use quantum dots for solar cells. So this would be important for next generation solar cells. Light emitting diodes, I think recently, relatively recently, they have been making quantum dot displays. And so next generation displays, light emitting diodes here. Anyways, let's continue. There are generally two classes of methods that people use to assemble nanoparticles. And so here's an assembly of a nanoparticle. This is the famous bow tie that a group has created. This is the Yang group. Anyhow, whatever the fabrication techniques are here, the main idea behind top-down methods is that they're using something to carve out some structure, and then of course that structure can eventually result in a assembly. In this situation here, they use PMMA, and they use an electron beam. High energy electron beams are shot down to the substrate, and it removes some of the substrate, and then they evaporate gold onto a surface, creating this gold film, and then they do some other processes to remove the resist in this case, and then that creates an assembly. And that is how they made this assembly here. Anyhow, there are many methods for top-down methods, carving out some structure on a substrate in order to assemble these nanoparticles. E-beam lithography is the most popular, mainly because it has a very useful advantage. The beam spot of the electron can be quite small, meaning they can design structures at nano precision at nanoscales, and they can pretty much move the electron beam how they would like. This means that they can create any complex 2D designs. However, there are some disadvantages, unfortunately. It turns out that it's very expensive to do, and it requires expensive equipment such as high vacuum, ultra high vacuum probably, and also like a clean room, things like that. Very difficult to work with. And of course, it's the top-down methods is you're creating a structure from carving out a structure from using some method, and of course, so you're limited to 2Ds, and you're limited to substrates, meaning you couldn't create these assemblies in solution, which would be useful as a biosensor, as an example. And so top-down methods are sort of analogous to wood carving, as I'm showing there. Anyhow, there's also bottom-up methods that overcome these disadvantages. Essentially, nanoparticles are functionalized somehow. They're functionalized because in bottom-up methods, we tend to eat components one by one together, and then we allow them to self-assemble. And of course, the driving force here is that these things are thermodynamically driven. Of course, there are also disadvantages as well. Again, our lab moves in this direction to assemble nanoparticles. In our lab, we essentially are pipetting machines. We ourselves are pipetting machines. In other words, we basically do normal laboratory work. And things are pretty inexpensive and relatively simple to do. Again, there is a disadvantage, and that disadvantage is that once you try, of course, nanoparticles, we use ligands to functionalize a nanoparticle, and the ligands tend to create a shell around the nanoparticle, and of course that would mean that if there's binding between ligands, like I'm showing here, two proteins are binding to each other, the the binding is isotropic. They can approach each other in different directions, and the shell of the ligands can bind with one another. And this causes different aggregations, as you can see here. Or we could call these assemblies as well. You can see different types of assemblies, smaller and larger. It's in the background here. And it's just an example. We would like to control these assemblies a lot better, and eventually I'll get to that point. But bottom-up methods are, again, we're putting components one by one together, so it's more, it's analogous to Lego building, for example. Anyway, so to overcome this disadvantage of isotropic binding because of the nature of the spherical ligand shell, we use DNA to do so. And so let's go ahead and talk about how that works. Again, functionalizing nanoparticles are necessary. This is such that so that we can direct these nanoparticles. We do functionalize them with single-stranded DNA, and a ligand shell is created. If we tailor the experiment properly, we can get different sets of nanoparticles functionalized with complementary strands so that they may bind. And this is what we call ligand shell hybridization. We use ligand shell hybridization in our methods. However, there is an issue. If you have many of these ligand shells hybridizing together, again, we're going to get these weird, uncontrollable aggregates because the shell is spherical and we have isotropic binding between DNA strands. To get around this, instead of having ligand shells binding or hybridizing, we prefer to have the ligand shells hybridized to a linker strand so we can get around this issue. And folks have done this. This is Alpha Sato's group. Of course, if this still is too simple, I guess you could create a dimer. And as you can see here, the gap distances are variable. So likely this assembly wouldn't really produce ideal coupling properties that we're looking for. Coupling properties are highly dependent on nanoparticle gap sizes. Anyhow, the simple assemblies they're too simple. We would like to create more complicated assemblies. And of course, it's difficult to control the gap sizes. So there is a way around this, and DNA origami is a process that you can use where you fold a long circular single-stranded DNA. Maybe we'll call this a scaffold. And of course, if we use short single-stranded DNA, we can use them to fold the scaffold and create some desired structure. And as you can see here, I'm showing that one of the staples can be designed so that it doesn't bind to the scaffold, so that you can create this overhang, and of course we can call that a capture strand, and of course then we can have those capture strands complementary to the functionalized nanoparticle ligand shell, and so then we can assemble the nanoparticles this way. So now you have two nanoparticles, a dimer, for example, in this diagram. And people have done this. They've created different nanoparticle assemblies using DNA origami. This is a common way to do so. Bottom up and relatively easy. Anyhow, there are still some issues with some of the designs of these origamis, and that is they still possess some floppiness. One-dimensional and two-dimensional DNA origami are still relatively flexible, and of course the tether that's formed at the capture strand, that is expected to have some flexibility. So you can imagine that the nanoparticles having some swiveling. Anyhow, I'm trying to show in this diagram that we will have some nanoparticle gap fluctuations if this is likely in solution. So yeah, of course it's going to give us a lower quality plasmonic or energy transfer device. And to get around this, our group uses a DNA origami cage, and we believe it has the proper constraints to reduce the floppiness. And so our cage does host the proper assembly that we're shooting for. And of course there is the correct, first off, the correct spatial arrangement, and of course the confinement. And of course I'll show you a picture soon of this. And of course there's going to be multiple tether points that will support a more rigid and less floppy assembly. And so this is the design that our group uses. It's a DNA origami cage represented by this cube structure. There are two openings, the front and the rear, and ligand shell hybridization is occurring, so we expect multiple DNA hybridization between the nanoparticles. The interior nanoparticle also is being held into the cage by 4 capture strands that are delocalized. They are not in just one region, they're surrounding the nanoparticle. And you'll see this very soon in a better 3D rendered image. And of course, yeah, we expect this process, this ligand shell hybridization via DNA origami cage, to be an improved assembly. Therefore, maybe possibly a higher quality device. Anyways, so let's look at some of the work that was done by former grad student Yihan Zhang. He does get a lot of credit for this. In his design, he created a DNA origami cage, as you can see here, and one of the first steps is to encapsulate a nanoparticle inside the cage. We call this encapsulation. As you can see, there are the 4 tether points. And then this is followed by ligand shell binding, and in this case here, because there are 2 openings of the cage, you may attach 2 larger nanoparticles, and this would create a collinear trimer assembly via ligand shell hybridization or ligand shell binding. The top view here, just to indicate the ligand shell binding between the exterior and interior nanoparticles. And of course, here is an SEM image of the product that he was able to assemble. All right, and so, but there, even all the issues that Yihan had were generally low yields. The encapsulation process, for example, had a lot of low yields. So this was a really big challenge for him. Generally, mainly we didn't have a method to study optimization conditions for better yields, as well as optimizing purification methods, and also trying to reduce time. The 36 hours here I put here is the annealing time that is required in the current protocol for the encapsulation of a nanoparticle. Anyhow, that would be the first step in this reaction, and then the second step here would be ligand shell binding. And in here, I'm trying to show that I'm interested at this point in just creating a dimer. I can control the mole ratios and hope to get good dimer yields. And of course, in order to really get to the ligand shell hybridization, I first do need better yields of encapsulation before I do this. So these are some issues that need to be considered. Reproducibility is also an issue. So first off, this long multi-step process, it's an inefficient way to try to determine where the optimizations are needed, because it takes a week to form this product, and so it's sort of a trial and error method. Change one parameter and carry out the reaction, and then you look at your product. It's very time consuming, and there's an infinite amount of parameters that we can play with. So I do put reproducibility here because at times I think Ihan found that he had difficulty in determining how a yield was achieved relative to other times. Anyhow, yeah, basically inefficient methods of finding optimization conditions for better yields, particularly. I do put time here because we might be interested in reducing the time as well. Anyways, so I have plans. My work is going to be trying to use FRET to study this because it's a more efficient way to determine an optimization condition, because this process of using FRET is real time and in situ. So the plan would be to tag one of the capture strands with the dye. And we can study this using two methods. One of the methods is, here I show the key just in case it's confusing, but one of the methods is if we use a quantum dot nanoparticle for encapsulation, we can initially excite the quantum dot because it fluoresces, and we would see it emit in the green for our particular quantum dot that we use. Now, if we may also, instead of using a quantum dot, we may use a gold nanoparticle. And if it is the gold nanoparticle, then we would prefer to excite the dye, which would emit in the red. Now, upon encapsulation, if it is the quantum dot, the green light that we see will disappear because now the quantum dot and the fluorescent dye are nearby each other, close enough for an energy transfer to occur, a non-radiative energy transfer. And so this results in the dye emitting instead. So we would see, for the quantum dots encapsulation, we would definitely see a change in, or an increase in wavelength, or an increase in fluorescence emission by the dye. Anyhow, and then of course, if the gold nanoparticle is used, it will be encapsulated, and its property is that it will quench the dye. So there would be no emission from the dye, and so we would see some fluorescence intensity decrease over time. So let's look at some expectations. If it's a gold nanoparticle, which the dye is being absorbed in this region, we would excite the dye, and upon encapsulation, we will see the fluorescence intensity decrease, and then over time, we can monitor this. So essentially, this is the rate of encapsulation decreasing over time, or the rate behavior of encapsulation over time. Anyways, and then of course, if it's the quantum dot dye FRET pair, then the quantum dot has a broad excitation wavelength in the UV. And of course, the quantum dot emits in the green, which should have good spectral overlap with the dye, shown in bold green here. And of course, then we would get some emission from the dye upon encapsulation. And of course, over time, we would see something like this. We would see the dye start to decrease in its intensity, and the fluorescent, the quantum dot decrease in its fluorescence intensity in the green here, and then the dye to increase. And so we would expect something like this if we're monitoring the dye's increase in fluorescence intensity. Again, it would be the result of this increasing intensity is the result of encapsulation. Okay, so if I'm able to get optimizations, my next step would be to study how this nanoparticle encapsulation is occurring with the DNA origami cage. First off, we know that these particles are negatively charged because DNA is negatively charged. So the ligand shell here would give the surface of the nanoparticle a negative charge, and of course the DNA itself is negatively charged. So we do expect repulsion Of course, this is in solution, so we do expect DVLO effects as well. So if I plot some whatever energy profile diagram here, we could see it looking something like this, where some transition state would be some high energy state here, and then upon encapsulation, reaching some minimum. I've thought about this a little bit, still thinking a lot, but if I mean, at this point, I'm thinking in Gen Chem. I just taught Gen Chem, so maybe I could do an Arrhenius plot because I should be able to back out some rate constants, and so maybe it's possible we could look at some actual numbers here. So just an example is, what if we, because the nanoparticle can enter the cage from either opening the front or the rear, and of course, we know that this pre-exponential factor here, letter A here, in the Arrhenius equation, depends on orientation. So what would happen if we close the rear end of the cage opening so that there's only one opening, so that the nanoparticle can enter? So now the orientation of the cages and nanoparticle collision needs to be very specific, and that would definitely change A, and it should match up to theoretical values, hopefully. And so that's just an idea. Anyways, so I do put here, we're talking about accessibility, so we're talking about the ease of a nanoparticle going inside to a cage. And lots of things to consider in these experiments. Of course, the smaller nanoparticle, we expect it to enter the cage a lot more easily, so higher accessibility. So we would expect higher yields and rates, or higher yields and rates, but how much higher are the yields going to be, and how much faster is the reaction going to be as well? We also want to know, of course, the cavity and nanoparticle size limitations. So if we have some cavity with a certain size, what are the ranges of nanoparticles that we can use to encapsulate? And then, of course, we would like to know other things. There are many other things to look at, but I list a few here only. So, for example, the number of capture strands. We currently have 4. And if we reduce the number of capture strands, does this affect encapsulation? And of course, also the capture sequence. That's something that may be important because we've been looking at poly-A single-stranded DNA, and maybe that can have some effect of sliding a particle into the cage a lot better. Anyhow, of course, after optimizations and being able to get some good yields of these encapsulated products, then I would like to study ligand shell hybridization using FRET. And in this FRET, the FRET pair is a quantum dot pair. So turns out that they both absorb light in the UV, and so we expect them to both emit. However, when a ligand shell binding occurs, then we expect energy transfer because, again, this assembly allows the nanoparticles to be close enough so that energy transfer, non-radiative energy transfer should occur. Basically, the oscillating dipoles couple. And so we can see that we would see a change in fluorescence intensity of each of the from each of the nanoparticles. So, of course, exciting the quantum dots in the UV, shown by the blue curve, and then both nanoparticles will emit. However, over time, due to ligand shell hybridization, we would see, in this case, red increase in fluorescence intensity and a drop for the green. anyhow, maybe we could see something like this. And again, this would be representative of ligand shell binding. The fluorescence intensity is change as a result of ligand shell binding, so we could back out some kinetic information. Anyways, so in summary, use FRET to optimize the conditions for the multi-step origami cage templated or heterodimer assembly. And of course, study excessive. From that, we would study, hopefully from those optimized conditions, we can study accessibility of nanoparticles for encapsulation. And one of the final, it's a capability gap, but we would like to show that DNA origami cages are going to be the next viable tools for studying energy transfer between quantum dots. Because quantum dots right now are a hot topic in their ability to transfer energy. Again, lots of applications that I mentioned before. All right, so let's now talk about my past year's work. Functionalized gold nanoparticles. Something that our lab is familiar with doing. Functionalized quantum dots. Learned how to use cat nano and can-do programming to generate staples. This is important because eventually I do want to make my own cages with different cavity sizes. And so I need to be able to learn how to create a DNA origami. And then of course I folded DNA origami. In our lab we tend to work with the DNA origami tile and DNA origami cage. And of course I have been able to fabricate a DNA origami tile conjugated nanoparticle. I've been able to attach nanoparticles to an origami. And of course I've also been able to attach gold nanoparticles to an origami cage. In this case, the encapsulation of the gold nanoparticle. Anyways, here are some functionalization results of gold nanoparticles. We use dynamic light scattering to determine hydrodynamic diameters and how they change before and after functionalization. So blue for 10 nanometer gold nanoparticles, green 30, and red for the 50. The dashed lines represent the unfunctionalized nanoparticle, and the blue or the solid lines represent the functionalized nanoparticles. The increase in hydrodynamic diameter is consistent with the size of our ligands. And so here are some values. DLS is also very good for determining how monodispersed or polydispersed our samples are as well. It can give us a really good idea on if functionalization was good or bad, or it would tell us also if there were aggregations that occurred, because it tends to happen with nanoparticles. Anyways, just a quick schematic on how this is working. You have a 10 nanometer gold nanoparticle, so this is essentially the smallest hydrodynamic size it can reach. And of course, we assume that the ligand shell that's formed, we can determine its maximum hydrodynamic diameter, excluding any water that is bound to this structure. And then, of course, we know what the sizes are of our single-stranded DNA. So then we can sort of figure out if it's consistent with our DLS hydrodynamic diameters. So as you can see here, it should be around or in between about 10 and 37. And for the 10 nanometer gold nanoparticles, I got 24.51. So that's pretty good. Anyways, and also I just show here that we're not entirely sure what the ligands are doing on the surface of this gold nanoparticle. There's likely to be some DNA strands that are that the bases have some affinity to the gold, so they might be wrapping a little bit around the gold nanoparticles. If there's a high enough density, they do tend to stand up, but we're not really interested in this at the moment, just because the ligand shell density the density of the ligands in the ligand shell is sufficient for our experiments, so we're not too worried about this. Of course, I've also functionalized quantum dots. I'm following the one-step ligand exchange protocol from Ramini, also from our group. Quantum dots that we buy from Sigma Aldrich are capped with octodecimine, and octodecimine is hydrophobic, so it's not going to dissolve in water, which is a requirement for the nanoparticles, so that the ligands, the single-stranded ligands that we want to attach onto them is possible. And so, as you can see here in this diagram, I'm just trying to show you that a phase transfer is required so that quantum dots can get functionalized. And we do use DMSO. Anyways, yeah, and I'm just showing you that here. And after we do carry out the phase transfer, we do add sodium hydroxide. We believe that we could get a higher density of ligands onto the nanoparticles if we deprotonate the hydrogen or the thiol. Removing that hydrogen creates a thiolate, and that thiolate has been shown computationally that it has a higher affinity to the different metals. And in this case here, our surface of these quantum dots are zinc sulfide. So we expect the thiolate to have a higher affinity to zinc. Anyways, here are some results I'll show. The phase transfer is here. On the right, I'll shake it. These two samples are the same. On the right, I'll shake it, and what you're going to see is a phase transfer. The bottom layer is the quantum dots in chloroform, and the above layer are the aqueous oligos. So as you can see, the phase transfer is occurring. Here you see that the nanoparticles are at the interface here stored, but over time, I don't show the whole process. You still need to shake this for 30 minutes on the vortex. But eventually the nanoparticles spread out in the aqueous layer. This is an example of adding sodium hydroxide to the sample afterwards. And of course we removed chloroform at this point already. And something else is happening here. I still have yet to check the fluorescence to see what is happening to the emission. It does look like the green color is turning yellow as the sodium hydroxide is dissolving or diffusing through the solution. And yeah, but still not sure. It could just be a change in PL, I'm not entirely sure. But definitely we'll be checking soon. This is the phase transfer and adding sodium hydroxide. Finally, we put this in a gel, the bare quantum dots don't move, and the functionalized quantum dots do move. However, there's a huge smear, so that's not a good sign. Smearing indicates that you may have many differently functionalized nanoparticles. What I mean is you have a variety of nanoparticles that have, let's just say, a broad distribution of ligands. I would go ahead and need to do more experiments in order to optimize this, to remove that smearing. I would also work with dithiol instead of monothiol. Romani was using monothiol in her work, and I'm now taking over and considering dithiol. Dithiol just has two sulfur groups as the anchoring head group to the surface of the nanoparticle. So we want to switch to dithiol because this is going to be a stronger ligand attachment, so we expect more stable assemblies. Anyways, it does show that a band was made there. Very different results here, so this was kind of promising for us. And I do compare these to non-thiolated oligos, poly A and poly T strands. Yeah, so over some time I've been able to optimize the dithiol so that I can get a single band. This helps us to indicate that, hey, all the nanoparticles tend to have similar mobility. Likely they have a similarly dense ligand shell. Some other data. The functionalized quantum dots in water, shown in orange here. It does show that there's some disturbances. Not sure why that is, of course, either. Obviously, we're putting new ligands onto a surface of a quantum dot, so we're disrupting that surface. We may even be etching that surface, and so we do expect some changes in their optical properties. I'm not sure if this is noise, or it doesn't look like it's noise because this is pretty high optical density, 0.1 for example. So, and we're seeing that noise up here as well. Anyway, so maybe it's not noise. This disturbance, we should call it, might be due to maybe other stuff that's inside the sample, maybe aggregates or something like that. We're not entirely sure. Anyways, DLS results after functionalization, the hydrodynamic diameter does increase again. This is good. So yeah, I've been able to functionalize with dithal. This is a relatively new thing in our group. I've also been able to fold a DNA origami. Well-known procedures already in the literature to how to do this. We use CAD Nano software. We need to design the structure so that we know where our helices are. So this is the blunt end, which means we're looking down at the helical axes when we in this view. And again, if you don't know, double-stranded DNA is often modeled as a rod, so we'd be looking down the rods. Anyhow, we need to fold scaffolds. Definitely don't need to go over the details, but there's ways to fold these scaffolds. If you don't know what you're doing, the program's going to give you errors, and it can be kind of frustrating. I'm just doing a tile here, single layer of DNA helices making a tile. And then, of course, we generate staples, shown in red. And then we use qhia to generate the simulated structure of it. Again, the rods are considered DNA helices. Yeah, so definitely we see some twisting happening here. Mainly it's because it's hard to, each time a crossover is formed, in order to bind the helices together, crossovers are needed, and those crossovers are not exactly at the correct positions maybe. And in addition, these holiday junctions are holding DNA strands, negatively charged double-stranded DNAs together, and so we get these global twists, and there are ways to get around that too. So in our processes, we take our staples and add them to our scaffold, we anneal it with some method, and we do produce a tile. We know how many helices there are, we know how many base pairs there are, we can get a good idea of the sizes. We then run them through a gel to separate out the excess staples that there are, and then we identify our tile, DNA origami tile. We cut it out as best as we can, and we spin them out in centrifuge. Anyhow, so for the DNA origami tile, I've been able to put nanoparticles on them. I'll first put on a quantum dot nanoparticle, and then after that, because right now I'm only interested in putting on a single nanoparticle as part of my work. There's an annealing method, and we add the tile to functionalize nanoparticles, and then we anneal them at some temperature program. We're using some temperature program. For the function of quantum dots, the gels do indicate that where the tile is, there is a band corresponding that overlaps that area, which we attribute to being quantum dots that are bound to the tile. So then we spin it out, and we use AFM to characterize it. And yes, it shows that these arrows here I'm showing here do have something in the center of them. I guess, for example, here, and of course we draw a height profile across here, and we do see that the abrupt height changes here represent the proper size of the nanoparticle to some degree. Of course, it's not an accurate height just because the tip might not be as sharp as we'd like. Functionalized gold nanoparticles, I've done this same process. The nanoparticle is a little bit bigger. These are 10 nanometer gold nanoparticles, so kind of see this thing happening here. It looks like a large blur because I believe the nanoparticle is sort of moving a little bit as the tip goes over it. And again, our tip may not be super sharp here, or it might not even be a new tip, because if we're just trying to verify if we've accomplished the conjugation between the nanoparticle and the origami, you know, we're not going to use a brand new tip. We're just trying to check to see if it was successful. I guess if we're going to do a figure set or something for a paper, then we would probably have to consider sharper tips. And I do want to thank nthuav for doing this. He helped me out on this a lot. Anyways, now let's talk about making a heterodimer, putting a quantum dot and a gold nanoparticle onto a tile. This is again Ramini's work that I'm continuing and trying to reproduce. The gels indicate that it's possible we get a band where the DNA tile is, an overlapping band where gold nanoparticles are also, pretty faint though, and also an overlap of where the functionalized quantum dots are. Now, because they are near each other, they may be quenching. However, we do expect to have some tiles with only quantum dots and also some tiles only with gold nanoparticles. It should be sort of a yield of each of these as side products. And also the quenching might not be 100% because I think Ramani showed that the quenching efficiency may not be that 100%. Anyways, I'm pretty confident the dimer was made. I just haven't verified it. Currently, I don't have skills in transition electron microscopy or SEM, scanning electron microscopy. As you can see up here, the Ramini's work, when she created this heterodimer, it was difficult to distinguish between the two nanoparticles because the tip itself is too big. However, electron microscope here, she used TEM, and of course you can see that a dimer is made on the above tile. Sometimes you would get, single nanoparticles only because, again, side products. All right, now let's talk about DNA origami cage. To hurry up and wrap this up, very complicated design to make. So thank you, Ihan, for this. We anneal it, some dimensions of our cages if you're interested. Run the gel, separate the excess staples, and determine and get your cages. Add your cages to your nanoparticles, anneal them, and run your gels to see if they show where DNA origami cages, also where gold nanoparticles are. And I did see that, so it's a good sign that I was able to encapsulate. I haven't verified yet because it may be difficult. Our lab only has an atomic force microscope, so it's a little bit difficult to see if we're looking at a nanoparticle that's inside of a cage with AFM. Anyways, I do show that I've matched, or somewhat matched, Ihan's work. This blue loading die here is actually one of the new loading dies that we were trying out. We're trying out different loading dies because we feel like it may be affecting the mobilities in the bands of origami, and so we were trying out a different loading die, and this loading die turns out to be in the same region where our gold nanoparticles go to. It may not be visible where there's a band here representing excess functionalized gold nanoparticles, but there is, and so I'm pretty happy that it works out, and that it kind of looks like Ihan's bands encapsulated on top with lower mobility and functionalized gold nanoparticles on the bottom. Again, the overlapping bands indicate that encapsulation should have occurred. I've also tried to make a 50 cage. What does that mean? That means that a 50 nanometer gold nanoparticle is attached to a single cage. And the single cage, and there's no encapsulated nanoparticles, so the binding is occurring through outer capture strands on the cage. And so if we take these gold nanoparticles and we attach them to a cage. And note that the cage has outer capture strands on the left side and on the right side. I'm hoping to get this. If this may occur as well, but I'm hoping that the amount is very little, and so my higher yield is single cage, single nanoparticle. If we add these in the appropriate molar ratios, we should get the correct product. Right now, I'm only aiming for the 1-to-1 here. There are other side products that may occur, which we don't want. So this is going to take some doing. I'm talking about this now because in the future, when I encapsulate a nanoparticle, if I wish to make a dimer in higher yields, I'm going to have to know methods in order to get a nanoparticle to just make a dimer and not a trimer with a nanoparticle inside. Anyways, yeah, these are some things you'd have to consider to parameterize to get these just right. Of course, we want to do a 1-to-1 molar ratio to get a single nanoparticle, single cage attachment. Play with time, concentration, and the annealing method. Anyways, I do show some gels here. I varied it, the ratios, the gold to nanoparticle cage, the gold nanoparticle to cage ratios are 6-to-5, 1-to-1, 1-to-25, and 1-to-2. I wanted, in this example here, I'm just trying to see if I can find a band for the 1-to-1. And so I'm showing that it's likely, it could be that the heavy band up here is the 1-to-1 product that I'm shooting for. I do show some numbers here. In the table above, it's just talking about concentrations and volumes I'm using. Anyways, I assigned the first band with 1 cage, 1 nanoparticle. However, it could be this band here might be an aggregate for all I know. I really don't know. And then of course the lower bands have more cages on them, and I believe this is the way to think about it, just because I'm increasing the amount of cages. The cages are in higher molar ratio than the gold nanoparticles, so I don't really believe that we'll be forming more of the structures you see above here, where there's multiple attached nanoparticles to each other, just because there's not as many of them, especially this 1-to-25 that I'm showing you here. Anyhow, I definitely don't believe this is true, though. I really don't know what's happening. And in the last band, I do assign to be the gold nanoparticle, because that's where the gold nanoparticle band is lining up with. Anyways, just to finish up, I'm not sure what's happening. I could, in the future, just put outer capture strands on one side of the cage and use that as a standard. And if I know where that band is, then maybe this structure is more likely to form a single nanoparticle, single cage structure. So if I can get a band from that, then I can know better if I've created it, if the band's lined up. Anyways, yeah, and of course the 50-50 cage. That would be something I would like to be able to do too, a 2-to-1 ratio. Anyways, and that's it for my talk.